Good morning students. In the last lecture we learned about the properties of the inductance. Today we are going to discuss a very important topic. It is nothing but the energy in the inductor circuit as well as the inductance of a solenoid. So we are starting from this equation, energy in an inductor circuit. So what is the energy? We know while a body performing linear motion, it possesses kinetic energy as well as potential energy, and it possesses the total energy. Okay, so in this inductor circuit there is some energy must be required or some work must be done to maintain the current in the inductor circuit, because whenever there is a current flowing through a inductor, a magnetic flux develops surrounding the inductor, and due to which an EMF induced in the circuit, and this EMF produces or induce a current which is opposite to the applied current. So to maintain the current in the inductor circuit, we need to supply some energy or some work must be done to maintain the EMF and to maintain the current in the inductor. So the energy or the work done to maintain the current in the inductor circuit, it is also known as the energy in the inductor circuit. So what is the expression for the energy in the inductor circuit? We know that what is the work done in the case of electrical circuit. What is the work done in the case of electrical circuit? The work done is equal to, it is dW is equal to EI multiplied by dt. What is the dW? This dW is nothing but a small work done when a current I is passed for a time dt. Okay, so this is the small amount of work done. Now we know that this E is nothing but the induced EMF in the inductor circuit, and this EMF is given by E is equal to minus L into di by dt. So what is the work done? Therefore this dW is equal to minus L into di by dt into I into multiplied by dt. So therefore this dW is equal to this minus L into this dt get cancelled, is I multiplied by di. So this is the small amount of work done to produce a current, induced current di into the inductor. Now this is a small work done. If we want to calculate the total work done, then we must be integrate this equation. Therefore by integrating this equation, this integration of d omega, which is equal to dW is equal to W, which is equal to integration of minus L I into di within the limit 0 to I0. Now why we taking this limit from 0 to I0? Because we have to maintain the current I0. We have to maintain the current I0 in the inductor circuit. So we take this lower limit as equal to 0 and the upper limit as equal to I0. So what is the work done? The work done W is equal to, this is minus L into this I square divided by 2 and the limit from 0 to I0, which is equal to, this W is equal to minus L into I0 square divided by 2, or we can also write this W is equal to minus 1 by 2 L into I0 square. Now if you want the magnitude of this work, the work is equal to 1/2 L I0 square. So this amount of work done in the inductor circuit to maintain a current I0 in the inductor. Okay, now suppose we keep a value I0 is equal to 1 I0 is equal to 1. Therefore, we can write this W work done is equal to 1 by 2 into L, or we can write this L is equal to twice of W. So, what is this? What this equation indicate, or what this equation represent? This equation represent that the inductance of a inductor is numerically equal to the twice of the work done to maintain the current in the inductor circuit. So this L is equal to twice W. It indicates that the inductance of a inductor in an inductor circuit is equal to twice of the work done to maintain the current in the inductor circuit. So L is equal to 2W. This is the equation of this energy in the inductor circuit. This is the main equation for the energy, because this is the equation for work done, and work done is stored in the form of energy. So we can also write this energy is equal to 1 by 2 Li0. Now if we know the equation of energy in a linear motion, kinetic energy is equal to 1/2 mv square. Okay, so by analogy we can say that the role played by the inductor in the electrical circuit is approximately equal to the role played by the mass in the linear motion, as well as the role played by this current I0 is equal to the role played by the velocity of the particle moving in a particular direction. So we can say that there is some analogy between the energies of the linear motion of a particle performing linear motion as well as the energy stored in the inductor circuit. Okay, so this is the energy in an inductor circuit. Now we are moving towards the inductance of a solenoid. So what is a solenoid? Solenoid is a structure in which a wire is wound on it and a current is passed through it. Then a magnetic field is developed along the core, along the hollow core of the solenoid. And we already learned about the magnetic field produced due to the current passing through the solenoid at the center. Okay, so we are now moving towards the inductance of the solenoid. Okay. In the last lecture, we learned about the concept of self-induction. What is self-induction? Self-induction is the production of EMF in the coil, induced EMF in the coil due to the change in the current in the same coil. Okay, so it is called as self-inductance. And in this self-inductance, this EMF, or we can say that this phi magnetic flux is equal to L multiplied by I, or we can also write this L inductance is equal to phi divided by I. So this is a simple equation, this is a simple relation between this inductance, magnetic flux and electric current. Now in the case of solenoid, a wire is wound on the upper part of the solenoid and a current is passed through the solenoid. Then due to the current, a magnetic field is developed along the core of the solenoid, and this magnetic field is given by, what is this? The magnetic field is given by, this magnetic field B is equal to mu 0 and I. This is the magnetic field produced at the center of the solenoid. Now we know that the inductance N is equal to phi multiplied by I. But suppose for a solenoid we are considering this L is equal to this N phi by I. What is capital N? This capital N is the number of turns. Number of turns in the solenoid. Okay, so this L is equal to N phi divided by I. Okay, where this N is the number of turns. Here we introduce or define a new term. This new term is small n, which is equal to the number of turns capital N divided by length, that is number of turns per unit length, that is equal to n upon L. So therefore we can write this capital N is equal to n multiplied by L. So what is this capital N? This capital N is the number of turns, this small n is the number of turns per unit length, and this small l is the length. What is small l? It is the length of the solenoid. So we can write this n is equal to nl in this equation. So we get this l is equal to nl into pi divided by pi. Now we know that the relation between magnetic flux and magnetic field is given by this phi is equal to, it is equal to B multiplied by A. What is A? A is the area of cross section, and this B is the magnitude of magnetic field. So this phi is equal to B multiplied by A, but we know that when a current is passed through a solenoid, the magnetic field produced at the center of a solenoid is given by B is equal to mu 0 n I. So we can write this L is equal to, L is equal to, this is NL into pi. What is pi is equal to? It is equal to B multiplied by A, and it is divided by current I. But what is the magnetic field produced at the center of the solenoid? It is equal to mu 0 n I. So we can write here this n mu 0 n I, okay, multiplied by L multiplied by A, and it is divided by I. So this I get cancelled, this I and I get cancelled. This is equal to mu 0 L A n square, or this inductance can be also write as this mu 0 L into A, or we can write this pi d square divided by 4 and is multiplied by n square. So this L is directly proportional to d square, and this L is directly proportional to n square by keeping all the terms constant. So what this equation indicate? This equation indicate that the inductance of a solenoid is directly proportional to the square of the diameter of the solenoid. As the diameter increases, the inductance of the coil also increases, as well as it is also depend on the number of turns per unit length, that is n square. So in this way we find out an equation for an inductance of a solenoid in which a current is passed through, and the solenoid having length L and area is equal to A. So in this way today we discuss about the energy in an inductor circuit, as well as we also learn about the inductance of a solenoid. Now in the next part we will see when the inductors are connected in series combination or they are connected in a parallel combination. So what is the resultant inductance and result in the series combination and in the parallel combination? So there are two conditions when the inductors are connected in series and inductor are connected in parallel. Then what is the effective inductance of the circuit? Okay, so suppose L1, L2, L3 be the inductance or inductor connected in series, then the resultant inductance Ls is equal to L1 plus L2 plus L3 up to the number of inductors connected in a series combination. Okay, so this is Ls is equal to L1 plus L2 up to Ln. If the value of each conductor, each inductor is L, so we can write this equal to L plus L plus L. But how many times? It is n times L, so it is equal to nL. So when the inductance of same inductance L are connected in series combination, the effective inductance Ls is equal to n multiplied by n. Now when these three inductors or n inductors are connected in parallel, then what happens? Then it is given by 1 by Lp is equal to 1 by L1 plus 1 by L2 plus 1 by L3 plus 1 by Ln. Now if the inductance of each inductor is equal to same, it is equal to L, so we can write this as N divided by L, or this Lp is equal to L divided by N. So this is the simple equation for a resultant inductance when the inductors are connected in parallel combination and series combination. In the next lecture we are going to discuss the concept of mutual inductance. So this is enough for today. Have a good day. Bye.